Section: Introduction. In this section, we discuss how aligning large language models, LLMs, with human values and intentions has proven to be an effective strategy. This usually involves fine-tuning the models using a substantial amount of synthetic data generated by LLMs or data annotated by humans. Recent research has particularly emphasized the importance of the quality of instruction data in this process. Many studies have contributed to improving the quality of instruction by focusing on making the input queries more diverse and complex, as well as enhancing the quality of the responses. These efforts can generally be categorized into two main strategies. The first strategy involves manually creating high-quality data. This method, while effective in generating complex queries and accurate, readable responses, is labor-intensive and difficult to scale. The second strategy seeks to automate the extraction of high-quality instructions from existing datasets, taking advantage of their wide availability. However, this approach often faces challenges such as the inclusion of factually incorrect information and the tendency for the format and style of responses to be influenced by the preferences of distilled LLMs. In our paper, we shift the focus from creating new instruction data from scratch to improving the quality of existing instruction data and aligning it more closely with human values. We introduce a straightforward yet effective method called REALIGN, which is distinct from the previously mentioned approaches. REALIGN requires a base instruction dataset, which can be sourced from large existing supervised datasets or publicly available instruction data compiled through various methods. The REALIGN process consists of three main steps. The first step is criteria definition, where we define human preferences for response formats and other aspects in natural language for 46 different scenarios. The second step, retrieval augmentation, expands the knowledge base for tasks that require extensive knowledge, such as open domain question answering and fact verification, by incorporating additional information to enhance the factuality and informativeness of responses. The third step, reformatting, aims to realign the responses with the established criteria and the gathered evidence, ensuring that the outputs are both well-structured and supported by evidence. Our approach redefines the roles of humans and LLMs in the alignment process, leveraging their complementary strengths. Humans specify their preferences, and LLMs reconstruct instructions based on their generative capabilities, without relying directly on distilled LLM knowledge. Through this collaborative effort, we aim to produce instruction data that is not only more contextually accurate but also more closely aligned with human preferences. We apply this method to 5 types of existing instruction data, including both general and mathematical datasets. The effectiveness of REALIGN has been demonstrated across various benchmarks, showing significant improvements in alignment, mathematical reasoning, factuality, and readability. Notably, REALIGN has shown a remarkable ability to enhance math reasoning skills, with significant improvements observed in specific benchmarks. In comparison to traditional methods of creating instructional data, which rely heavily on human annotation and are difficult to scale, our proposed method offers a way to automatically improve data quality with minimal labor and fewer factual errors. This represents a significant advancement in the field of LLM alignment and instruction data quality improvement. Section Summary. In this section, we introduce the concept of REALIGN, a method that focuses on enhancing existing instruction data quality to better align with human values. REALIGN involves defining criteria for preferences, augmenting retrieval to improve factuality, and reformatting responses to align with established criteria and evidence. By leveraging human preferences and ILM's generative power, REALIGN significantly boosts math reasoning and general alignment abilities with minimal data, offering automatic data quality improvement and reduced factual errors compared to traditional methods. Section: Instruction Selection. In this section, we delve into the process of instruction selection, which has gained significant attention following the realization that quality is all you need. Our goal here is to sift through a vast amount of instructional data to identify and select a small subset of the highest quality samples for use as a training dataset. We assess the quality of these datasets by measuring the loss on an evaluation dataset against natural language indicators. Some approaches we discuss include directly using ChatGPT to score the data, while others suggest scoring the data using a trained model to reduce costs. We also explore tagging samples within SFT datasets based on their semantics and intentions. This allows us to define instruction diversity and complexity in terms of these tags to better rank the data. Additionally, we introduce a self-guided method that employs a new metric, instruction following difficulty, IFD, to evaluate data by identifying discrepancies between a model's responses and its autonomous generation capabilities. This involves training two separate scorers to assess the complexity of the instruction and the quality of the response, respectively, and then determining the diversity based on the distance between embeddings to select high-quality data. However, it's important to note that these methods often rely on distilled datasets due to their large scale, which comes with the inherited drawbacks of distilled data, including the potential for hallucinations by large language models, LLMs. Moving on to instruction tuning, our focus shifts towards enhancing the model's ability to follow instructions and aligning LLMs with human values. Initially, instruction tuning was primarily aimed at improving cross-task generalization capabilities by increasing the quantity and diversity of tasks. However, recent efforts have shifted towards extending these capabilities to more generalized scenarios, particularly those involving real-world questions, without explicitly defining tasks. Our approach is distinct in that we leverage the future of the task to design a better format for it, thereby improving the quality of the data. In the REALIGN section, we introduce a method aimed at enhancing the quality of responses within a base instruction dataset, which consists of input queries and their respective responses. This method involves three key steps: defining criteria including tasks and formats for each task, augmenting the retrieval of relevant external information for knowledge-intensive tasks, and reformatting the original response based on a combination of handwritten formats and the retrieved information. We emphasize the importance of clearly defining tasks to subsequently devise tailored formats, as the optimal format varies across different tasks. We categorize 46 distinct tasks into 10 major groups and develop tailored formats for each, considering factors such as organizational structure and output modality to ensure readability. For knowledge-intensive language tasks, which require substantial external knowledge to ensure factuality, we select 5 tasks for retrieval augmentation. We use the Google Search API to retrieve the most relevant information, which is then filtered to serve as evidence for enhancing the responses. This step makes the responses more factual and informative. Finally, we discuss the rewriting step, where we employ large language models, such as ChatGPT, to rewrite the response based on the specified format and retrieved evidence. This adaptive strategy ensures that the rewritten response not only meets specific formatting requirements but also incorporates specified information, thereby enhancing the overall quality and relevance of the response. Section Summary. In this section, we focus on instruction selection, where we aim to choose high-quality samples from a large dataset by evaluating their quality using natural language indicators and a new metric called instruction following difficulty, IDF. We also introduce instruction tuning to enhance models' instruction following abilities and align them with human values, and REALIGN, a method that improves response quality through criteria definition, retrieval augmentation, and reformatting based on task-specific formats. Section: Non-knowledge intensive tasks. In this section, we discuss our approach to handling tasks that don't require a lot of specific knowledge, like generating stories or poems. We noticed that these kinds of tasks don't fit well into a one-size-fits-all format. So, we decided to rework parts of these tasks. We did this by taking the original task responses and reorganizing them with the task query and a specific format through a prompt, resulting in a revised response. When it comes to tasks that do require specific knowledge, we add an extra step. Besides reorganizing the original response with the task query and format, we also include any relevant information we've found that could help answer the query. This helps make the response more accurate and informative. We also noticed a problem with the length of responses after reformatting. Sometimes, the reformatted response would be much shorter than the original, which wasn't ideal. To fix this, we decided to only use the reformatted response if it wasn't less than half the length of the original. If it was shorter, we'd stick with the original response. To further improve the quality of our tasks, we set up specific rules for filtering tasks based on their content. This was to prevent errors from spreading when classifying tasks. For example, if a task involved coding or planning, we would keep the original answer. After applying these methods, we ended up with a revised dataset, which we call the REALIGN dataset. It's a collection of reorganized task queries and responses. For evaluating our approach, we chose 2 manually created datasets and 1 generated dataset to test how well our method works for general tasks. The Open Platypus dataset combines 11 open-source datasets to help improve performance in STEM and logical reasoning tasks. The No Robots dataset contains high-quality instructions and demonstrations, and the Alpaca dataset is generated from a model and contains instructions for various tasks. We also selected 2 additional datasets specifically for testing math reasoning skills. We chose 2 well-known models for fine-tuning our approach, Llama 2 to 13b and Mistral 7b. These models are open source and represent the current state-of-the-art in language modeling. Our evaluation focuses on how well our method aligns with general and specific requirements, including math reasoning, factuality, and readability. For general alignment, we use widely recognized benchmarks and employ GPT 3.5 and AutoJ for one set of evaluations due to the high cost of using GPT-4, which is known for its strong correlation with human judgment. For specific alignment, we look at math reasoning by fine-tuning our models on specific math problem datasets and testing their accuracy by comparing the final number in their responses to the correct answer. To assess factuality, we randomly select cases from a public question and answer dataset and rate them on a scale from 1 to 10 using GPT-4, considering the question, response, and verified answer. Section Summary. In this section, we differentiate between non-knowledge intensive tasks, where we rewrite parts of tasks like story and poem generation due to their non-standardized nature, and knowledge-intensive tasks, where we incorporate retrieved evidence. We also address issues like length filtering and task-based filtering to ensure data quality. Additionally, we evaluate our REALIGN model on various datasets for general alignment and specific alignment abilities, including math reasoning, factuality, and readability. Section: Readability. In this section, we delve into the evaluation of readability by contrasting a model trained on the original dataset with another model that has been enhanced with REALIGN. We utilize both human and GPT-4 evaluations on the Vicuña Bench dataset for this purpose. The Vicuña Bench dataset is particularly suitable for this comparison because it contains fewer complex questions, such as those involving code and math, allowing the evaluators to concentrate more on the format than the content. To ensure a fair assessment, we crafted an evaluation prompt that emphasizes readability and randomized the response positions to prevent any bias. Moving on, we explore the impact of REALIGN on the general alignment ability of models. Through experiments conducted on Alpaca Eval, MT Bench, and Vicuña Bench, we observed an improvement across almost all datasets and benchmarks for both the Llama 2 to 13b and Mistral 7b models. This indicates that REALIGN can significantly enhance the quality of models' responses and their conversational capabilities. Notably, the results from MT Bench reveal that REALIGN can also improve the performance of the second turn in conversations for half of the datasets, despite only rewriting the first turn of the instruction data. We also investigated the effect of REALIGN on math reasoning by applying it to the GSM-8K and math datasets. The results were quite impressive, showing a substantial boost in math reasoning abilities on both datasets, with an increase of up to 9.86% on GSM-8K using Llama 2 to 13b. This improvement is not just limited to specific datasets. REALIGN also enhances cross-domain performance, as evidenced by the notable improvements in GSM-8K test results when models are trained using the math dataset, and vice versa. A key factor behind this improvement is REALIGN's ability to provide clear intermediate steps and explanations, which in turn strengthens the model's reasoning capabilities. In terms of factuality, we applied REALIGN to the Open Platypus, No Robots, and Alpaca datasets using Llama 2 to 13B and compared the responses to ground truth in NQ samples. The findings highlight an elevation in factuality, underscoring the effectiveness of REALIGN. This enhancement is likely attributed to the incorporation of retrieval augmentation. Regarding readability, we employed a readability evaluation prompt to guide both GPT-4 and humans in comparing the model trained on the original dataset with the model trained with REALIGN. The results showed that REALIGN can improve the readability of responses across 3 datasets, particularly in the Open Platypus dataset, where there was an 18.7% improvement in GPT-4 judgments. This demonstrates that tailoring different formats for different tasks and reformatting them can significantly enhance readability. Interestingly, humans tended to provide more ties in their judgments compared to GPT-4, possibly because REALIGN offers a better structure, which might limit GPT-4 to surface formats, neglecting content and deeper structure. In contrast, humans can read more carefully, not being confined to surface formats. We also conducted a dataset analysis, comparing the change in response length, measured in the number of tokens, between the original datasets and those enhanced with REALIGN. We found that responses in the Open Platypus dataset became shorter, while those in the No Robots dataset did not change significantly, and responses in the Alpaca, GSM-8K, and Math datasets became longer. Additionally, we calculated the percentage of responses for which the adaptive rewriting method selects rewrite by edit distance. Specifically, we measured the edit distance on a word basis, then divided this by the length of the longest response, original or rewritten, to obtain the edit rate. Responses with an edit rate greater than 0.2 were classified as rewritten, and the rest as unrewritten. For the GSM-8K and Math datasets, all data were considered rewritten as adaptive rewriting was not applied to them. Lastly, we examined the potential trade-off between knowledge and alignment abilities when models are fine-tuned on the REALIGN dataset. To assess the knowledge ability, we used benchmarks such as Big Bench Hard, BBH, and AGIVAL, which are knowledge-intensive QA tasks. The results indicated that REALIGN has little to no adverse effect on knowledge-based tasks, suggesting that our approach does not compromise the knowledge contained in the original dataset. In some instances, REALIGN even significantly boosted knowledge, such as in the Open Platypus dataset on AGIVAL. This could be due to the fact that a well-defined format can improve the accuracy of knowledge-based tasks and that the retrieval of external information can enhance knowledge. Section Summary. In this section, we evaluate the impact of REALIGN on readability, alignment ability, math reasoning, factuality, and knowledge ability in various datasets and benchmarks. REALIGN significantly enhances response quality and conversation ability across different datasets, boosts math reasoning performance by providing clearer explanations, and improves factuality by adding retrieval augmentation. Additionally, REALIGN demonstrates the ability to enhance readability by restructuring responses, especially evident in the Open Platypus dataset, showcasing improvements in GPT-4 judgments and highlighting the importance of designing different formats for different tasks. Section: Ablation Studies. In this section, we delve into the process of conducting ablation studies on the Open Platypus dataset by creating 2 different versions and training them using the Llama 2 to 13B model. Our first variation involves removing the retrieval augmentation from the REALIGN process, which means we rewrite all tasks without including any evidence. The results, as displayed in the table, show a decrease in the general alignment ability, knowledge ability, and factuality score. This drop highlights the importance of retrieval augmentation. Interestingly, we observed that the factuality scores are actually higher when retrieval augmentation is not used compared to the original dataset. This suggests that REALIGN could also have a positive impact on improving factuality. In our second variation, we eliminate the adaptive rewriting feature from REALIGN and instead apply a forced rewriting approach. The table indicates that this change leads to a decrease in both general alignment and knowledge ability. This outcome likely arises because forced rewriting, despite making the responses more structured, fails to take into account the specific requirements of the question, thereby diminishing the model's ability to follow instructions. However, we noticed an increase in the factuality score, which could be due to forced rewriting generating a larger volume of realigned data. This increase in data volume introduces more retrieved knowledge, potentially enhancing factuality. We also explore the scaling law of REALIGN by experimenting with different amounts of realigned data. Specifically, we randomly select a certain percentage, K%, with K being 0, 5, 10, 20, and full, where full represents 29.9% of REALIGN alpaca data to include, and fill the rest with original responses. With 0% corresponding to the original alpaca dataset, our findings are quite fascinating. Just 5% of realigned data results in a 67% improvement in general alignment ability compared to using the entire realigned dataset. This indicates that a small fraction of data is sufficient to learn the style and format, thereby unlocking the knowledge and capabilities already present from the pre-training phase. Moreover, as we increase the percentage of realigned data used, we continue to see improvements in knowledge capability. Lastly, we present a case study from the MT bench test set. This example demonstrates that the response generated by the REALIGN model is better formatted, showcasing the effectiveness of our approach in enhancing the quality of responses.